Good morning students. In this video we are going to discuss about two types of extrinsic semiconductors, that is N-type semiconductor and P-type semiconductor. We already studied extrinsic semiconductor means semiconductor crystal which is doped with impurity atoms. So based on the impurity atoms that we are adding, the semiconductors can be categorized into N-type and P-type semiconductors. Okay. So first let us see what are N-type semiconductors. N-type semiconductors are the semiconductors which is doped with a pentavalent impurity. That means the tetravalent atoms, semiconductors are actually tetravalent atoms, that means silicon or germanium. They are doped with the pentavalent impurities such as phosphorus, arsenic, antimony, etc. They belong to group 15. Semiconductors are belong to group 14. So this belong to group 15. So phosphorus, antimony, phosphorus, arsenic, antimony, etc. Then we can say those semiconductors are N-type semiconductors. Now, how that semiconductor is formed? That is what we are going to discuss today. Pentavalent element means, what is the valency? Valency is 5. What is the valency of a tetravalent element? 4. So silicon and germanium are having valency 4, whereas phosphorus, arsenic, antimony, they are having valency 5. Now just look at the figure, we will see how things happens. In N-type semiconductor, suppose I am doping germanium with arsenic. So arsenic atom is having 5 valence electrons. Out of 5 valence electrons, 4 electrons of the arsenic will form covalent bond with germanium atoms. Okay? 4 electrons of the arsenic form covalent bond with 4 germanium atoms. Now you can see here a 5th electron is left free. This electron cannot make any bond. This electron is left free. That electron will stay in a very small energy level which is marked here with a dash line. Okay. So like that, if I dope the germanium with 1000 arsenic atoms, 1000 electrons will be set free. For one arsenic atom, 1 electron is left behind, which is unpaired. Similarly, if I dope with 1000 arsenic atoms, 1000 electrons will be remaining unpaired. All those unpaired electrons, all those free electrons will stay in this energy level. This energy level is called donor level. And we have already studied the forbidden energy gap between the valence band and conduction band. That means this energy gap. This energy gap is 0.74 electron volt for germanium. Now you just see this energy gap. This gap is very less, which is 0.054 electron volt. So as I told, if there are electrons lying here, a very small energy of the order of 0.045 electron volt is required for those electrons to jump into the conduction band and becomes free electrons. Okay. So initially when that electron is formed which is unpaired, that electron will stay somewhere in the lattice and all those electrons will achieve a different energy level which is called donor level. Now a very small energy, that is of the order of 0.045 electron volt, is required for the electron in the donor level to move towards the conduction band. So conduction can be increased. if they ask you to draw the energy band diagram of n-type semiconductor, you need to draw this diagram. This is only for the understanding, no need to draw this diagram. You have to draw this diagram if they ask energy band diagram of n-type semiconductors. So as I told, the energy required to detach the fifth loosely bound electron is only of the order of 0.045 electron volt for germanium. Now, a small amount of energy provided due to thermal agitation is sufficient to detach this electron and it is ready to conduct the current. The force of attraction between this mobile electron and the positively charged impurity ion is weakened by the dielectric constant of the medium. So, such electrons from the impurity atom will have energies slightly lesser than the energy of electrons in the conduction band. Therefore, the energy state corresponding to the fifth electron is in the forbidden gap slightly below the lower level of the conduction band. In the exam, they will ask a question like this: where is this donor energy level lying? You can see donor energy level is lying just below the conduction band. So, they will ask why that donor energy level is lying below the conduction band. The reason is this. The reason is this: due to the dielectric constant of the medium, the force of attraction between the mobile electron and the impurity ion is weakened. Such electron will have the energy which is slightly lesser than the energy of electrons in the conduction band. That is why the donor energy level is lying just below the conduction band. Okay, so they can easily move towards the conduction band by giving a small energy. So, this energy level is called donor level, and n-type semiconductor is also called donor type semiconductor. Now, we are going to see the carrier concentration in n-type semiconductors. Listen, till now we have been studying like this: when we dope, electrons are getting free, loosely bound electrons are there and they are lying in the donor energy level. Have any holes formed in this case? No, till now no holes are formed. Till now no holes are formed. Now, when we give more and more energy, for example, we are heating the semiconductor. Heating is called thermal agitation. When we heat the semiconductor, what will happen? More and more electrons will receive the energy and they will break the covalent bond and they will jump from valence band to conduction band, as we studied in the case of pure semiconductor. The same thing happens here also. As a result, some more electrons are formed, thereby creating some holes in the valence band. So, I can say like this: in n-type semiconductor, the electrons are formed by two ways. The first one is by doping, many electrons are formed, that is lying in the donor energy level. Number two, by thermal agitation, some more electrons are formed, that is moving from valence band to conduction band directly. So, free electrons are formed due to doping and due to thermal agitation, two things, whereas holes are formed only due to thermal agitation. So, here the electron carrier concentration will be more and hole charge carrier concentration will be less. Therefore, I can say like this: in n-type semiconductor, electrons are the majority carriers and holes are the minority charge carriers. Okay. So, here it is written: in n-type semiconductor, free electrons are the majority charge carriers and holes are the minority charge carriers. They will ask the reason. You have to copy this, the first and the second paragraphs. Now, at any instant, if you take Ni into Pi or N into P, N means charge concentration of electrons and P means charge concentration of holes. So, N into P is equal to Ni square. And we already studied Ni and Pi are the intrinsic carrier concentration of pure semiconductors. And Ni and Pi is Ni equal to Pi, we studied in pure semiconductors. That is why I wrote N into P is equal to Ni into Pi, which is equal to Ni square. So, the rate of recombination of electrons and holes is proportional to N and P, or we can say it is proportional to the product of N into P. Okay. And for a fixed temperature, for a given temperature, the product N into P must be a constant. Now let us move to the next type, which is P-type semiconductor. So what is a P-type semiconductor? P-type semiconductor is an extrinsic semiconductor in which a tetravalent element, that means silicon or germanium, tetravalent element is doped with a trivalent impurity. So, semiconductor like silicon or germanium is doped with a trivalent impurity such as indium, boron, gallium, etc. Those atoms have the valency of 3. So, they are called P-type semiconductors. So, semiconductor crystal which is doped with trivalent impurities, that means in periodic table it belongs to group 13. They are called P-type semiconductors. Now let us see how this is formed. Suppose I am taking indium. And indium is introduced into the germanium crystal. So, indium is our dopant here, and how many valence electrons indium has? 3. So, the 3 valence electrons of the indium form covalent bond with 3 germanium atom, this and this. Now, to complete the covalent bond, we need one more electron which is deficient, which is not there. Indium is having 3 electrons only, 3 valence electrons only. So, that will form covalent bond with these 3 germanium atom, but in order to form the 4th covalent bond, there is a deficiency of electron. Then what will happen? We have to overcome this deficiency, right? For that, a covalent bond from the neighboring silicon bond will be broken. Okay? So, whenever this deficiency happens, in the valence band, the covalent bond between 2 silicon atoms will break and electron will jump from that silicon covalent bond towards this deficiency and complete the tetrahedral structure, thereby creating a hole in the valence band of silicon covalent bond. I repeat once more. Whenever a deficiency happens here, from neighboring silicon bond, a covalent bond will be broken and electron from that place will jump towards this lattice and complete this deficiency, thereby creating a hole in the silicon covalent bond in the valence band. So, valence band is created with a hole now. Okay, this hole is actually responsible for conduction. Now remember, like the thing like this, I just doped with one indium. How many hole I created in the silicon covalent bond in the valence band? I created one hole. Similarly, if I dope with 1000 indium atoms, I can create 1000 holes in the valence band of silicon-silicon bonding. So here we are creating holes in the covalent bond, in the valence band of the silicon-silicon bond. So whenever I say hole, you can think it is the deficiency of electron. So in order to fill that hole, we need electrons. Electrons need to be taken. Only then the holes is filled. Therefore, I will mark like this. All those deficiency, those holes will lie in this region, which is called acceptor level, because they need to accept the electrons to complete to fill those holes. Therefore, the acceptor energy level which arises due to the creation of holes will lie somewhere just above the valence band, and the energy gap between the valence band and the acceptor level is 0.05 electron volt. Then what will happen? If I give a very small energy, due to that small energy, electrons from the valence band will be broken and those electrons will jump towards this acceptor level and fill those holes. That is how the conduction happens. Okay? When we give a sufficient amount of energy, say for example 0.05 electron volt, a very slight energy, that time itself the electrons from the valence band will break the bond and they will jump towards the acceptor energy level and fill the holes in the acceptor energy level. This is how conduction takes place. So you can copy these as the notes itself. So the trivalent impurity atom is called acceptor atom because it accepts the electrons from the silicon-silicon covalent bond. The acceptor impurity produces an energy level just above the valence band. This energy level is called acceptor energy level. Now here also we can, these all are the things which we explained just now, so you can just copy these things. Now here also N into P is same as Ni into Pi, which is Ni square. Okay. Now in P-type semiconductor, the holes can be created by two methods. The first one due to doping, second one due to thermal agitation. Whereas here electrons can be created only due to thermal agitation. So in P-type semiconductor, holes are the majority carriers and electrons are the minority carriers. Just the reverse of N-type semiconductor. In N-type semiconductor, electrons are the majority carriers, holes are the minority carriers. Whereas in P-type semiconductor, holes are the majority carriers and electrons are the minority carriers. So here which current is more, electronic current or hole current? Yes, hole current is more here. In P-type semiconductor, hole current is greater than electronic current. Whereas in N-type semiconductor, electronic current is greater than hole current. I have just made a table for the distinction between extrinsic and intrinsic semiconductor. Everything we have already discussed, so you can just copy this from the board. See here I already told, no, in intrinsic semiconductor the conductivity is very less, here conductivity is increased, and here conductivity is increases with the rise in temperature, and here conductivity depends purely on the impurity added. So we can add the impurity and controls the conductivity. That is the idea behind extrinsic semiconductor. And here Ni equal to Pi always, and there we can control Ni and Pi by depending upon the doping. Okay. So copy these 4 points. Similarly, see the next one, distinction between semiconductor and metal. Semiconductor behaves like an insulator at 0 Kelvin, whereas metals, it remains conductors itself, and when temperature increases its conductivity will increase, whereas in metals the conductivity decreases with rise in temperature. Now the conductivity increases with rise in potential difference applied, whereas in metal conductivity is an intrinsic property and is independent of the potential difference. So think about that point. For metals, conductivity is independent of the potential difference, whereas here it depends on the potential difference. It increases with increase in potential difference. Semiconductors does not obey Ohm's law. That means you will not get a straight line graph here, whereas conductors obey Ohm's law, metals obey Ohm's law. Now doping the semiconductors with impurities vastly increases the conductivity, and whereas in metals making alloy with another metal decreases the conductivity. So that is the difference. Okay, that is all for today's topic. Bye.